I welcome my friends to this little tutorial on playing with our horizontal asymptotes. So using Desmos.com just to put in some different functions and start to think about it and really make some predictions and test what we know and kind of figure out more about horizontal asymptotes and what they equal. And what the first thing you want to remember is with horizontal asymptotes, we're not really discovering exactly what the function is, the value of the function, but what we're trying to figure out is what the function is going to become close to, all right? That's why I'm highlighting that. What it's going to become close to, and I can't stress this enough, at its very outer edges. So we're just looking at the function as x, or the domain, the x values, as it moves out to infinity. What does the function tend to equal? It's not going to exactly equal it, it's going to approach it. That's what asymptotes are. So always remembering that when x is not infinity, like when it's numbers like 1 and 2 and 3, that function may definitely cross that asymptote, maybe even more than once, I don't know. But I know from experience it definitely can cross the asymptote, but then it will always in the end come back to where you think it should be, as long as your thinking is correct. So let's look at three different basically three different scenarios that will lead us to different types of asymptotes. The first one is when the highest exponent is in the denominator. And just thinking about that for a moment in your mind, I bring up on Desmos what I did. I give an example. I have this highest exponent. I have an x to the cubed in the denominator. I have a 3x in the numerator, the plus ones and all the other stuff. It shouldn't really matter if you think about it, as x becomes really, really big, and then once x hits x is like 100, once you take 100 and you cube it, then that's going to completely dominate. So the denominator is going to get very big, and even as the numerator does get bigger, clearly because x goes to 100 or 1,000, the bottom becomes so much bigger, so much faster that you're taking a number like in my little things to think about. You're taking a number like 5 and then you divide by 10. That's a half. That's pretty small. But then if you take 5 and divide by 100, that's even smaller. Or 5 divided by 1,000. So as the number gets bigger on the bottom, then the top number, it's going to dominate. So the horizontal asymptote should go to 0 always, whenever you have that. So you could try a few different ones. See what happens when you make this minus. See, it changed it, it kind of flipped it. But notice this one. I love this one because look, it does cross the asymptote. It crosses up temporarily. It does some funky things, but it comes back in the end. And so you can like play around with signs and just think about it. You don't want to just like throw numbers in, but you want to kind of think about what's going to happen depending on if I put minuses or pluses or that kind of stuff. So that's the first example. Try it for your own, then you can come up with one that works for you. The second example is when you have exponents in the numerator and denominator of the same order. And if you think about that and you try a few, what's you're going to discover is the coefficients of the that are in front of the highest x. Those coefficients are going to rule out in the end. So let's see an example. I did an example here. Open that up. So I have an example here with I have a very simple one: 4x squared on top and 2x squared on the bottom, and that function itself is just a line. And if you think about it, that's if you divide these two things, the x's are going to divide off. I'm just going to have 4 over 2. So in other words, y equals 4 over 2, which is y equals 2. Right? That's what that graph is. So this isn't good enough. I need to do something to make this a little more interesting. Just add x to it. There. Now, by doing that one thing, I make this a more interesting rational function. And what happens, of course, is as x gets really big, the x part, this one isn't really going to matter. It's going to disappear. You're going to be left with is just the 4x squared over the 2x squared. The x squared is going to divide off. You're going to be just left with the coefficients. And if you want to think about it, I'm going to leave this graph y equals 2 on there to see that horizontal asymptote. Just think in your mind, like, what if x is 10? If x is 10, I want to have 10 squared is 100. 4 times 100 is 400. Down here, I have the same thing. I have x squared. So 10 times 10 is 100. And this time, I multiply by 2. So on the top, I have 4 times that x value, which is pretty big. On the bottom, I have 2 times that same x value. So the same x value in the top and the bottom are going to disappear. But on top, I'm going to still have that 4 times, and the bottom I'm going to have 2 times. So that's why the coefficients will determine the value of the horizontal asymptote. So just to verify that, let's say I wanted to move it up to 6. If I want to move it to 6, I'm going to have a 12 on top. And sure enough, you see that when I put that 12, you can see the horizontal asymptote. It's going to go right to 6. Or I want to make it negative. How about negative 6? I could just stick a negative in front of it, and then bam, Horizontal asymptote is down here, -6. So pretty good. All right, final scenario is going to be the exponent of the numerator is of 1 degree higher than the denominator. This is where those funky oblique asymptotes come from. And hopefully you remember this, or if not, practice a few of these. You can find the equation of the asymptote, the exact equation, by dividing the denominator into the numerator, and you're just going to ignore the remainder. So let's see, I set up one for that. There. Let me open up that one. Example 3. So I have a polynomial on top that's of 1 degree higher. It's x squared. The bottom is just plain old x. So if you divide x plus 2, the denominator, into this, whatever it comes out should be the equation of the horizontal asymptote. So I'm just going to try to do this, and hopefully you can follow along as I say this out loud. On a piece of paper, you could write it out. Divide x plus 2, long division, into the numerator. So x is going to go into x squared x times. So that's my first part of the equation. So that's going to be, I'm going to write it out as I go. It's going to be x. And then I'm going to multiply x times x is x squared. X times 2 is 2x. So I'm going to have x squared plus 2x. And I'm going to subtract. I'm just doing the long division here out loud. 5x minus 2x is 3x. So I'm going to have a 3x left. So now I'm going to divide x plus 2 into 3x. Well, x goes into 3x 3 times. So on top, I'm going to have x plus 3. That's going to be the equation. Now I'm going to have a little remainder left because of the -12, but you don't worry about that. So the equation of the horizontal asymptote should be x plus 3. And so graphed x plus 3, you can see, as you zoom out, that indeed does appear to be the asymptote. So just think in your head, what if I want to move that asymptote from 3 up to, say, 5? Or if I want to change the slope of that asymptote. So let me do that first. If I want to change the slope is coming from here, right? So if you put a number in front of this, a coefficient, if I put a 2, that should make the slope go to 2. So you can see how I changed the function. That asymptote is no longer good. But if I come down here and put a 2, there you go. I got the new asymptote. So the slope of the asymptote is coming from the ratio, if you will, between the two leading coefficients. So if I put it like a 2 here, I'm going to come back to a slope being 1. And there it is. And you can see that's a good example across the asymptote, but it's going to come back to it if you go far enough. There it goes. Looks like it's coming back to it. But then now it's a little trickier to figure out how to move this up and down, how to move the y-intercept. That's coming from here, so it's coming from this minus this. So if you think about it that way, if I put a 5 here, then that should go right through the origin. So if that's up, then that should be 0. And that should be my new asymptote. And look, there it is. So if you're not following what I'm doing at the end here, just you can do a bit of math in your mind there. Play a little bit with this one and see if you can you want to start to be able to figure out how you can move this asymptote up and down so you can change the y-intercept, and also how you can play with the slope of that intercept. So that was the whole idea, just to play around and try different things out and start to get a feel for this.